Hello, friend. Welcome back. Or perhaps, welcome for the first time. Either way, I'm glad you're here. Some nights the world feels wider than it should. Stars breathe slower. Time folds in silence. Maybe that's just the mind listening to itself. Or maybe it's something more. Have you ever noticed how a single scent can pull you backward through years? How a song can make you feel 14 again, standing in your childhood bedroom, sunlight slanting through the window in a way it never quite does anymore. You weren't trying to remember, but suddenly you were there, not imagining it, not thinking about it. You were there. And for just a moment, time didn't move forward at all. It bent. It circled back. It whispered your name. Tonight we're going to explore something quietly miraculous. The physics hidden in remembering. The science of time travel that happens every single day inside the soft architecture of your mind. Before we begin though, if you find comfort in these quiet journeys, you might like to stay a while. You can gently tap the like button, subscribe if you'd like more stories told softly, and ring the little bell, not for noise, but so the next quiet night can find you again. Thank you for being here. Now let's drift. The question we're dancing around tonight is this: is memory just memory? Or is it the only form of time travel we'll ever truly know? Not the kind with machines or wormholes or spinning cosmic strings, but the kind that happens in the dark behind closed eyes when the day finally releases you and the past comes creeping back in. Scientists have spent decades trying to understand how we move through time. Einstein showed us that time bends, that it stretches and compresses depending on speed on gravity on the curvature of space itself. But long before Einstein, long before anyone wrote equations about space-time, human beings knew something else. We knew that time doesn't just move forward, it echoes, it loops, it lives inside us. Let me tell you about a woman named Jill Price. In the early 2000s, researchers at the University of California, Irvine, began studying her brain. Jill had a condition so rare that only a few dozen cases have ever been documented. It's called hyperthymesia, total autobiographical memory. If you gave Jill a date, any date from her past, she could tell you what day of the week it was, what she wore, what she ate for breakfast, what song was playing on the radio. She didn't try to remember, she just did. Always, endlessly. Her past wasn't behind her, it was with her. Every moment layered on top of every other moment, like glass panes stacked so thick, she could barely see through them to the present. Most of us don't live like that. Our memories blur, they fade, they shift and reshape themselves every time we touch them. And maybe that's a gift, because Jill described her condition not as a superpower, but as a burden. She couldn't let go, couldn't move on, couldn't forget the small embarrassments, the old heartbreaks, the ordinary Tuesdays that should have dissolved into time but didn't. She was trapped in her own past, a time traveler who couldn't stop traveling. But here's what fascinated the scientists. Jill's brain wasn't physically different, not in any dramatic way. Her hippocampus, the region responsible for forming new memories, was slightly larger than average. But so are the hippocampi of London taxi drivers who memorize thousands of streets. The difference wasn't structure, it was process. Something about the way Jill's brain encoded time, stored, it retrieved it. Something about the relationship between her neurons and her sense of self. And that's where the mystery deepens. Because memory, it turns out, isn't a recording. It's not a video file stored neatly in some neural archive. It's a reconstruction. Every single time you remember something, your brain is building that memory again from scratch, taking fragments, sensory details, emotions, context, and weaving them back together into something that feels whole, feels real, feels true. But is it? In the year 2000, a neuroscientist named Karim Nader conducted an experiment that changed how we think about memory forever. He worked with rats, training them to associate a sound with a mild shock. The rats learned quickly. Hear the sound, freeze in fear. Classic conditioning. But then Nader did something unexpected. He triggered the memory, made the rats hear the sound again. And in that moment, while the memory was active, while it was alive in their neurons, he injected a drug that blocked protein synthesis. The drug didn't erase the original learning. It erased the memory of remembering. The next day, the rats heard the sound again. And they didn't freeze. The memory was gone. Not because it was deleted, but because it had been interrupted mid-reconstruction, like a book being rewritten and someone spilling ink across the page before the words could dry. This process is called reconsolidation, and it happens in human brains too. Every time you remember your wedding day, your first kiss, the funeral you attended last year, you're not accessing a fixed record, you're rebuilding it. And in that rebuilding, things can change. Details can slip. Emotions can shift. You can remember something that never quite happened the way you think it did. Your uncle's voice at the dinner table. Was it really that loud, that sharp? Or has time made it so? Your mother's smile in that photograph. You remember it so clearly. But when you look at the photo again, her expression is different than you thought. Memory is creative. Memory is unstable. Memory is time travel. But the map keeps changing every time you try to read it. And yet, we trust it. We build our identities on it. We tell ourselves stories about who we are based on where we've been, what we've survived, what we've loved and lost. But what if those stories are written in sand? What if every time we revisit them, the tide comes in and smooths the edges just a little more? Does that make them less real, or does it make them more human? Neuroscientists at MIT discovered something beautiful and unsettling. They found that they could implant false memories in mice. They could make a mouse remember being shocked in a place where it had never been shocked. The memory felt real to the mouse. It behaved as if the trauma had happened. Its neurons fired in the exact same patterns they would have if the event were true. So, where does that leave us? If the brain can't tell the difference between a real memory and a constructed one, if the neural signature is identical, then what is truth? What is past? Maybe time isn't something we move through. Maybe it's something we carry. And every night when you close your eyes and drift into sleep, your brain begins its quiet work, sorting through the day, deciding what to keep and what to let dissolve, strengthening some synapses, weakening others, editing the story of you. Some researchers believe that dreams are part of this process, that when you dream of your childhood home, when you dream of faces you haven't seen in years, your brain is traveling backward through its own archives, not to observe, but to reorganize, to make sense, to find patterns, to hold on or to let go. There's a structure deep in your brain shaped like a seahorse called the hippocampus. Its name comes from the Greek, hippos meaning horse, campos meaning sea monster, the seahorse. And it is in its own way a kind of sea monster, because it holds the ocean of your past. It's where time becomes memory, where the present becomes something you can return to. In 1953, a man named Henry Molaison underwent surgery to treat severe epilepsy. Surgeons removed large portions of his hippocampus on both sides of his brain. The seizures stopped, but so did something else. Henry could no longer form new long-term memories. He lived in a perpetual present. Every conversation was new, every face unfamiliar, even if he'd met them 10 minutes before. He could remember his childhood. He could remember events from before the surgery. But after nothing stuck, time moved forward for everyone around him. But for Henry, it pooled, stagnant. He was a man unstuck not in the romantic science fiction sense, but in the saddest, most human way imaginable. He couldn't travel through time because time for him had stopped being a place he could go. And yet, here's the strange thing. Henry could still learn, not facts, not names, but skills. Procedural memory, it's called. You could teach him to solve a puzzle, and each day he'd get faster, even though he had no memory of ever seeing the puzzle before. His hands remembered what his mind could not. Somewhere deeper than conscious thought, time was still writing itself into his neurons. Just not in a way he could access, not in a way he could feel. Does that count as memory? Does that count as time travel? Or is it something else entirely? Something older, quieter, written in the language of muscle and instinct rather than thought. When you remember something, anything, your brain doesn't light up in just one place. Memory is distributed, scattered across regions. The hippocampus helps bind it all together, but the sites are stored in your visual cortex, the sounds in your auditory cortex, the emotions in your amygdala, the sense of self, of personal history in your prefrontal cortex. To remember is to gather, to pull fragments from across the vast neural landscape and hold them just for a moment in the light of consciousness. And then, when you're done remembering, those fragments scatter again, waiting, patient, until the next time you call them home. So, maybe memory isn't time travel in the way we imagine it. It's not going back. It's not seeing the past exactly as it was. It's more like receiving a letter from someone you used to be, written in handwriting that looks almost like yours, but not quite. Describing events you think you remember, but the details are softer now, blurred at the edges. The letter is real, but it's also been folded and unfolded so many times that some of the words have worn away. And maybe that's okay. Maybe that's what it means to be human, to carry time inside you imperfectly. To travel backward not with precision, but with feeling, with longing, with the quiet understanding that the past isn't a place you can return to. It's a place you rebuild every time you try. Tonight, as you rest, your brain will do what it does best. It will sift through the day. It will decide what matters. It will strengthen the synapses that hold the moments you'll want to keep. The laugh of a friend, the warmth of sunlight, the taste of something sweet. And it will let the rest fade gently into the background hum of your life. You won't notice it happening, but it will. Time folding itself into you, becoming memory, becoming story, becoming the quiet architecture of who you are. In the sections ahead, we'll drift deeper into this mystery. We'll explore why time only moves in one direction, at least as far as the universe is concerned. We'll talk about Einstein, about black holes, about the strange ways your brain bends time when you're afraid or joyful or lost in flow. We'll wander through paradoxes and wormholes, through déjà vu, and dreams through the science of now and the physics of remembering. But for this moment, just hold this thought. You are a time traveler, not someday, not in theory, right now. Every memory you hold is a journey backward. Every hope you carry is a journey forward, and the only moment you truly inhabit, the only moment that's real in the deepest, most physical sense, is this one. The one where you're breathing, where you're here, where time for just a little while feels like it might slow down enough for you to catch your breath. There's something the universe refuses to do, something so fundamental, so absolute, that it shapes every moment of your existence without you ever noticing. The universe will not go backward, not even once, not even for a second. Eggs don't unscramble themselves. Waves don't leap back up from the shore into perfect spheres of water. Your coffee never unmixes from the cream. And you, no matter how much you might wish, it cannot return to yesterday. Not really, not physically. The question is, why? What is it about the nature of reality that makes time feel like an arrow, always flying forward, never turning back? The answer lives in a concept so simple, so quietly devastating, that when you truly understand it, the whole universe starts to look different. It's called entropy, and it might be the closest thing we have to a law that governs time itself. Let me take you back to Vienna, 1870s. A man named Ludwig Boltzmann sits in his study staring at equations. He's trying to understand heat. Why does a hot object always cool down? Why does cold never spontaneously become hot? Why does disorder always increase? Boltzmann realizes something extraordinary. Heat isn't a substance, it's motion. The jittering, vibrating, chaotic motion of countless tiny particles. And when you have a system, any system, it naturally moves from order to disorder, from structure to chaos, from low entropy to high entropy. Not because there's a force pushing it, but because there are so many more ways to be disordered than to be ordered. Imagine you have a deck of cards perfectly arranged. Ace through king, hearts, diamonds, clubs, spades. Beautiful. Ordered. Now shuffle it once. The order breaks. Shuffle it again and again and again. What are the chances that after 1,000 shuffles, the deck will spontaneously return to perfect order? Mathematically, they're not zero. But they're so close to zero that you could shuffle once per second for the entire age of the universe longer than the universe has existed, and you still wouldn't see it happen. That's entropy. That's the arrow of time. Not a law that says you can't go back, just a law that says the odds are so astronomically against it that for all practical purposes, backward doesn't exist. Boltzmann called this the second law of thermodynamics. In any closed system, entropy always increases. Disorder always grows. The universe is slowly, inevitably, irreversibly spreading itself thinner, cooling down, leveling out, moving toward what physicists call heat death, a state where everything is the same temperature, the same density, the same nothing, where no energy flows because there's nowhere left for it to flow to. That's the far future, trillions upon trillions of years from now. But it's written into the fabric of reality. Time has a direction because entropy has a direction. And that direction is forward, always forward. But here's where it gets strange. The fundamental laws of physics don't care about time's direction. If you watch a planet orbiting a star and you play the video backward, the equations still work. Newton's laws are time symmetric. So are Maxwell's equations for electromagnetism. So is Schrödinger's equation for quantum mechanics. Even Einstein's general relativity, the theory that describes how space and time curve around mass and energy, doesn't prefer forward over backward. You could, in theory, reverse every particle's momentum in the universe, flip time's arrow, and the laws would still hold. The math doesn't break. The universe doesn't care. So, why do we? The answer seems to be initial conditions. The universe started in a state of incredibly low entropy. The Big Bang wasn't chaotic. It was smooth, uniform, almost perfectly ordered. And ever since, entropy has been increasing. That's why we perceive time moving forward. Not because the laws demand it, but because we started in a very special, very unlikely state, and we're sliding down the entropic hill toward equilibrium, toward disorder, toward the most probable arrangement of everything. Time's arrow isn't a feature of physics. It's a feature of history, of the specific way our universe began. But what does this mean for you? For your life? For your memories? It means that every moment you experience is a moment of increasing entropy. Every breath you take, every thought you think, every movement you make adds a little more disorder to the universe. Your body is a temporary pocket of order, maintained by consuming energy, by eating, by breathing, by breaking down the chemical bonds in food, and using that energy to keep your cells organized. But even that order comes at a cost. Every calorie you burn adds heat to the world. Every heartbeat increases entropy somewhere. You are in a very real sense a beautiful temporary rebellion against the universe's tendency toward chaos. And someday that rebellion will end. Your body will stop maintaining its order. Entropy will win, as it always does, as it always must. Does that thought make you uncomfortable? It shouldn't, because entropy is also why you exist at all. Without entropy, without the arrow of time, there would be no cause and effect, no memory, no growth, no change. The universe would be static, frozen, eternally the same. It's the flow from order to disorder that allows complexity to emerge. Stars form because gravity pulls gas together, creating pockets of low entropy that burn bright for billions of years before scattering back into space. Life emerges because chemistry finds ways to surf the gradient to capture energy as it flows, from high concentration to low, from the sun's nuclear fire to the cold of space. You are a pattern carved into that flow, a temporary eddy in the river of entropy. And when the pattern dissolves, the river continues. Indifferent, unstoppable, eternal. Now, let me tell you about an experiment. In 2011, physicists at the University of Maryland managed to violate the second law of thermodynamics. Sort of. They took a single atom of ytterbium, trapped it in a laser, and carefully measured its energy. Then they did something clever. They applied a pulse of energy in such a precise way that the atom's entropy decreased. For just a fraction of a second, disorder went down instead of up. Time's arrow in that tiny system flickered backward. But here's the thing. The act of measuring the atom, of controlling it, of applying the pulse that required energy, that created entropy somewhere else. In the lab, in the equipment, in the physicists' bodies as they breathed and thought and moved. The total entropy of the system, including everything, still increased. The second law held. It always holds. You can cheat it locally for a moment if you're very careful. But the universe keeps score, and the universe always wins. So, does this mean time travel is impossible? Does it mean we're trapped forever, moving forward with no hope of return? Well, that depends on what you mean by time travel. If you mean, can we reverse entropy? Can we unscramble the egg? Can we make the wave leap back into a perfect sphere? Then no. Not without spending more energy than you gain. Not without creating more disorder than you fix. But if you mean, can we move through time at different rates? Can we skip forward? Can we bend the flow? Then the answer is yes. Absolutely. Because while entropy gives time its direction, relativity gives it its flexibility. And that's where things start to get truly strange. Think about this. Right now as you listen, time is passing for you at 1 second per second. That sounds obvious, trivial, but it's not. Because 1 second per second is only true relative to you, in your reference frame, moving at your speed in your gravitational field. Change any of those variables, and time changes too. Einstein showed us that time is not a universal constant. It's not a river that flows the same for everyone. It's more like a fabric stretching and compressing, depending on how you move through it, how deep you sink into gravity's well. Two people can experience time at different rates, and both of them are right. Both of them are living through their own present moment, their own second per second. But those seconds are not the same length. If you stood next to a black hole, time would slow down for you, relative to someone far away. Not because you feel slower, not because your thoughts drag, but because space-time itself is stretched so severely by the black hole's gravity that every tick of your clock takes longer when measured by someone else's clock. From your perspective, nothing changes. You feel normal. Time feels normal. But to an outside observer, you're moving in slow motion, aging slower, experiencing fewer seconds than they do. And if you could survive falling into a black hole crossing the event horizon, the point of no return time would do something even stranger. It would stop, not for you. You'd still experience time, normally still have, thoughts still move forward toward the singularity at the center. But to anyone watching from outside, you would freeze. You would appear to hover at the event horizon forever, your image slowly redshifting into darkness, never quite falling in. Time's arrow bent so sharply by gravity that it stops making sense. Here's a fact that might surprise you. Every time you climb a flight of stairs, you age slightly faster than someone who stays on the ground floor. Because you're farther from Earth's center. Because gravity is slightly weaker up there. Because time for you ticks just a tiny bit faster. The difference is measured in nanoseconds, billionths of a second. You'll never notice it, but it's real. GPS satellites have to account for it. They orbit high above the Earth, where gravity is weaker, and their clocks run faster than clocks on the surface, about 38 microseconds faster per day. If we didn't correct for that, your GPS would drift off by miles within a week. Time dilation isn't science fiction. It's engineering. It's part of the infrastructure that runs your daily life. And yet, despite all this flexibility, despite the fact that time can stretch and compress and slow and stop, it never reverses. Entropy still increases. The arrow still points forward. Even inside a black hole, even in the most extreme gravitational fields we know of, disorder still grows. Cause still precedes effect. The egg still breaks. You still age. You still remember the past and anticipate the future, never the other way around. The universe, for all its strangeness, still insists on this one rule: forward, always forward. But why? Why can't we remember the future? Why does cause always come before effect? Some physicists believe it's because of the way information works, because memory is a record, and records require low entropy states. If the universe were high entropy, if everything were already maximally disordered, there would be no way to encode information, no way to store a record of the past. The fact that you can remember breakfast this morning is only possible because the universe started in a low entropy state and has been increasing ever since. Your brain is riding that wave using the flow of entropy to create structure, to hold patterns, to remember. If time's arrow reversed, you wouldn't remember the future. You wouldn't remember anything. Consciousness itself might not be possible. Because consciousness, like memory, is a process that requires order, emerging from disorder, patterns carved into the flow. There's a thought experiment called the reversibility paradox. Imagine you could take a film of the universe, every particle, every interaction, and play it backward. According to the laws of physics, it should work. Time, symmetric, remember. But here's the problem. If you play it backward, entropy decreases. Broken eggs reassemble. Heat flows from cold to hot. The universe becomes more ordered, which violates the second law. So either the laws are wrong or something about reversing the universe is impossible. Most physicists believe the latter, that the initial conditions matter, that you can't just flip the sign on time and expect the same universe to emerge. The past is written into the structure of the present, and the present is writing the future. There's no undo button, no reset, no rewind. Does that make you sad? The idea that time only goes one way, that you can't undo mistakes, can't relive perfect moments, can't go back and change the things you wish you'd said or done differently. Maybe. But consider this. If time didn't have an arrow, if entropy didn't increase, you couldn't learn. You couldn't grow. You couldn't become. Every moment would be isolated, disconnected from every other moment. There would be no narrative, no story, no you. The arrow of time is what gives your life meaning, because meaning requires sequence, requires cause and effect, requires the possibility of change. And change, my friend, only happens in one direction. Yet, even as the universe insists on moving forward, even as entropy marches on, there's something almost miraculous happening. Inside that chaos, inside that relentless slide toward disorder, complexity blooms. Galaxies form, stars ignite, planets cool, life emerges, consciousness awakens. You, a collection of atoms obeying the same laws as everything else, somehow find yourself here, thinking about time, wondering why it flows the way it does. And maybe that's the real mystery. Not why time has an arrow, but why in the middle of that arrow's flight beauty appears. Why order, temporary and fragile though it may be, finds a way to exist at all. So the universe won't rewind. But something else can. Something quiet and entirely human. And it happens not in the fabric of space-time, but in the soft folds of your brain, where physics gives way to something stranger, something we're only beginning to understand. Picture this: two clocks, identical in every way, built by the same hands wound with the same precision, ticking at the same steady rhythm. You place one on a table, you take the other on a journey, a flight around the world. When you return, you set them side by side, and they no longer agree. One clock is ahead, the other behind. Not by much, just a few hundred nanoseconds, a fraction so small you'd never notice it in your lifetime. But it's there, measured, verified, real. Time itself has split. Not because the clocks are broken, but because time is not what we thought it was. It doesn't flow the same for everyone, everywhere. It bends. it stretches, it slows. And the man who showed us this, who gave us the equations to prove, it changed everything we thought we knew about reality. His name was Albert Einstein. In 1905, Einstein published a paper that would fracture our understanding of the universe. It was called On the Electrodynamics of Moving Bodies, though history knows it better as the theory of special relativity. Einstein was 26 years old, working as a patent clerk in Switzerland, scribbling equations in his spare time. He had no access to fancy laboratories, no team of researchers, no experimental data of his own. Just thought, just imagination, just the willingness to ask a question that seemed absurd. What if the speed of light is always the same no matter how fast you're moving? What if it's not relative but absolute? The implications were staggering. If light always moves at the same speed, roughly 186,000 miles per second, then something else has to give. And that something is time and space. They're not fixed, they're not separate. They're woven together into a single fabric called space-time. And when you move through space, you also move through time. Faster motion through space means slower motion through time. Not metaphorically, not as a side effect, but fundamentally, measurably, undeniably. The faster you go, the slower time passes for you relative to everyone else. This effect is called time dilation. And it's not a theory anymore. It's a fact we've tested over and over again, with clocks, with particles, with satellites, with our daily lives. Let me tell you about an experiment. October 1971. Two physicists, Joseph Hafele and Richard Keating, board commercial airliners with 4 cesium atomic clocks. These are the most precise timepieces humanity has ever built, accurate to within billionths of a second. Hafele and Keating fly eastward around the world, then westward, while identical clocks remain on the ground in Washington, D.C. When they land, they compare the clocks. The ones that flew east have lost time, 59 nanoseconds to be exact. The ones that flew west have gained time, 273 nanoseconds. The differences match Einstein's predictions almost perfectly. Time aboard the planes moved at a different rate than time on the ground, not because of turbulence or pressure or mechanical failure, but because of motion, because of velocity, because Einstein was right. But why? What is it about speed that changes the flow of time? The answer lies in the constancy of light. Imagine you're on a train moving at half the speed of light. You shine a flashlight forward. To you, the light moves away at its normal speed. But to someone standing still watching the train pass, the light from your flashlight is also moving at the same speed. Not faster even though the train is moving, not slower, exactly the same. For that to be true, time on the train must be passing slower than time on the ground. Your seconds are longer than their seconds. Your watch ticks slower than their watch. Not because your watch is broken, but because time itself has stretched. This isn't magic, it's geometry. The geometry of space-time. Einstein showed us that space and time are not two separate things. They're coordinates in a 4-dimensional continuum. 3 dimensions of space, 1 of time. And just like you can rotate an object in space, turning length into width and width into depth, you can rotate through space-time, turning some of your motion through time into motion through space. When you're sitting still, you're moving through time at maximum speed, 1 second per second. But when you start moving through space, some of that motion gets redirected. You're still moving through space-time at the same total speed. But now part of it is spatial motion, and less of it is temporal motion. Time slows down for you, because you're spending some of your motion budget on space instead. The faster you go through space, the slower you go through time. Now, here's where it gets beautiful, and strange, and more than a little unsettling. This effect is real, but it's also completely unnoticeable at everyday speeds. When you drive your car at 60 miles per hour, time slows down for you, but by how much? By about 1 part in 10 trillion. You'd have to drive for your entire life to lose even a microsecond relative to someone standing still. The effect only becomes significant when you approach the speed of light. At 90%, light speed time passes about half as fast for you as for someone at rest. At 99%, time slows to about 1/7. At 99.9%, it slows to about 1/22nd. And as you get closer and closer to light speed time, for you approaches zero. Not quite reaching it, but asymptotically approaching it like a curve that never quite touches the axis. This leads to something called the twin paradox. It's not really a paradox, more of a thought experiment, but it captures something profound about time. Imagine two twins, both 20 years old. One stays on Earth, the other boards a spaceship and travels to a star 10 light years away at 99%. The speed of light then returns. From Earth's perspective, the journey takes about 20 years. But aboard the ship, because of time dilation, only about 3 years pass. When the traveling twin returns, they're 23. Their sibling is 40. Same DNA, same birth date. But one is aged 17 years more than the other. They've lived through different amounts of time. And both are correct. There's no objective clock that says who's really older. They've simply traveled different paths through space-time, and those paths had different lengths in the time dimension. Does this sound like science fiction? It's not. It's been measured. Muon's tiny subatomic particles are created when cosmic rays strike Earth's upper atmosphere. Moons are unstable. They decay in about 2 microseconds. At the speed they're traveling, even close to light speed, they should only make it about half a mile before decaying. But we detect them at sea level, miles below where they were created. How? Because from the muon's perspective, time has slowed down. In Earth's reference frame, the muon lives longer than 2 microseconds because it's moving so fast. From the muon's perspective, it still only lives 2 microseconds, but the distance it has to travel has contracted. Space itself has shrunk. Both explanations are true. Both describe the same reality from different viewpoints. Time dilation and length contraction are two sides of the same coin. And then there's gravity. Einstein didn't stop with special relativity. 10 years later, in 1915, he published General Relativity, which extends these ideas to include gravity. And what he found was even stranger. Gravity isn't a force pulling objects together. It's a curvature in space-time itself. Mass and energy bend the fabric of space and time, and objects move along the curves. And here's the crucial part. Where space-time is curved, time passes differently. The stronger the gravity, the slower time flows. This is called gravitational time dilation. And it's not a small effect. It's measurable. It's significant. It's part of the universe's structure. If you stand at the base of a mountain, time moves slower for you than for someone at the peak, because you're deeper in Earth's gravitational well. The difference is tiny, about 90 nanoseconds per day for every kilometer of altitude. But it's real. Physicists have measured it using atomic clocks, placing one on a table and lifting the other just 33 centimeters higher. The higher clock ticked faster, not by much, but measurably, undeniably faster. Gravity was pulling on time itself. Now, take this idea to its extreme. Imagine a star much more massive than our sun collapsing under its own gravity. As it shrinks, the gravitational field at its surface becomes stronger and stronger. Time for an observer on that surface slows down more and more relative to someone far away. Eventually, the star crosses a threshold called the Schwarzschild radius, and it becomes a black hole. At the boundary, the event horizon time dilation becomes infinite. Time stops. Not for someone falling in. From their perspective, they cross the horizon in finite time, experiencing nothing unusual at that moment. But to an outside observer watching from a safe distance, the infalling person appears to slow down, to freeze, to hang at the edge of the horizon forever. Their image growing dimmer and redder as light struggles to escape the gravitational pull. They never seem to fall in. They never cross. Time for them has stopped. This isn't theoretical. We've observed this. In 2019, the Event Horizon Telescope captured the first image of a black hole's shadow, the supermassive black hole at the center of the galaxy, M87. Around the black hole, we see light from matter spiraling inward, time stretched and bent by gravity so severe that space itself is dragged along, rotating with the black hole's spin. This effect is called frame dragging. Space-time near a rotating black hole is not static. It's twisted, swirling like water going down a drain. And anything near the black hole, even light, even time itself, is pulled along with that rotation. Time doesn't just slow down. It curves, it spirals, it becomes part of the black hole's rotation. But you don't need a black hole to experience gravitational time dilation. You're experiencing it right now. Your feet closer to Earth's center are aging slightly slower than your head. The difference is infinitesimal, about 90 femtoseconds over the course of a day. That's 90 quadrillionths of a second. You will never notice it. Your body will never notice it. But it's there, built into the structure of reality. Time flows slower the deeper you sink into a gravitational well. This isn't metaphor. This isn't approximation. This is how the universe works. And here's the really unsettling part. There is no universal now. No single present moment shared by everyone everywhere. Right now, as you listen, someone on the International Space Station is experiencing a slightly different flow of time than you. Someone in a basement is experiencing a different flow than someone on a mountain. Someone moving fast is experiencing a different flow than someone standing still. All of these presents are real. All of them are valid, but they're not the same. Time is local, personal, dependent on where you are and how you're moving. The idea of a single universal timeline where everyone experiences the same moment at the same time is a fiction. A useful one for everyday life, but a fiction nonetheless. Does this mean we can time travel? In a sense, yes. If you could travel at near light speed, or if you could orbit close to a black hole, you would move into the future relative to everyone else. You'd age slower. You'd experience less time. When you return, decades or centuries might have passed on Earth, but only years for you. You would have traveled into their future. But here's the catch. You can only go forward, not back. Time dilation lets you skip ahead, but it doesn't let you rewind. The arrow of time, entropy's arrow, still points in one direction. You can stretch time, you can compress it. You can slow it down to almost nothing, but you can't reverse it. Forward is still the only way. Or is it general relativity? Einstein's equations are time-symmetric in certain solutions. There are configurations of space-time where closed time-like curves exist, paths through space-time that loop back on themselves, returning to the same point in both space and time. In theory, if you followed one of these curves, you could travel into your own past. The equations allow it. The math works. But physics is not just math. Physics is what actually happens. And every solution that permits closed time-like curves requires something we've never seen: negative energy, or infinite mass, or exotic matter with properties that violate other fundamental laws. The universe seems to conspire against time travel to the past, almost as if it's forbidden, almost as if there's a rule we haven't discovered yet that says no, you cannot break causality. You cannot return to your own history. You cannot change what has already been. And maybe that's for the best. Because if you could travel backward in time, if closed time-like curves were possible, then paradoxes emerge. Not just philosophical puzzles, but genuine logical contradictions that might tear at the fabric of causality itself. We'll explore those paradoxes soon enough. But for now, let's sit with what we know. Time is not a river flowing at the same rate for everyone. Time is a dimension woven with space, flexible and strange and profoundly personal. You can stretch it. You can bend it. You can move through it at different rates depending on how fast you go and how deep you fall into gravity's embrace. Einstein gave us this gift, the gift of understanding that time is not absolute, that it's relative, that it belongs to you, shaped by your motion, your position, your path through the universe. But if time can bend in the presence of mass, if it can slow in the presence of speed, then what happens inside your mind, where thoughts move faster than light, where a memory can pull you across decades in an instant, where the past and future collapse into the single burning point of now? Close your eyes for a moment. Not now, of course, but imagine it. When your eyes are closed, when the world goes dark, how do you know time is still passing? You can't see the clock. You can't watch shadows move across the floor. And yet, somehow, you know. 5 seconds feels different from 5 minutes. An hour feels different from a day. There's a clock inside you, not mechanical, not precise, but present. Always ticking, always measuring, always constructing the feeling of now. The question is, where is it? Where in the 3-pound universe of your brain does time actually live? The answer might surprise you, because unlike your heart, which has a single pacemaker node that sets its rhythm, your brain has no master clock, no central timekeeper sitting in some neural throne room ticking away the seconds. Instead, time in your brain is distributed, scattered, emergent. It arises from the interaction of millions of neurons firing in patterns and rhythms, in waves that somehow mysteriously give rise to your experience of duration, of sequence, of the relentless forward march of moments. Time in your brain is not measured, it's constructed, built moment by moment from the raw materials of neural activity. And sometimes, just sometimes, the construction goes wrong. Time stretches, time compresses. Time bends in ways that Einstein never predicted, because the physics of space-time and the neuroscience of time are two very different things. One is about the universe. The other is about you. Let me tell you about a researcher named Warren Meck, who spent decades at Duke University studying how the brain keeps time. Meck worked primarily with rats, training them to press a lever after a certain duration had passed. 10 seconds, 20 seconds, 40 seconds. The rats learned quickly. They developed an internal sense of when to press accurate to, within a second or two. Then Meck started manipulating their brains. He used drugs, lesions, electrical stimulation, trying to find where the clock lived. What he discovered was fascinating. The clock wasn't in one place. It was everywhere. The striatum, a region deep in the brain associated with movement and reward, seemed to play a key role. So did the cerebellum, the wrinkled structure at the back of the brain, responsible for motor control and coordination. So did the prefrontal cortex, the seat of planning and decision-making. Time, it seemed, was not localized. It was a network property, an emergent phenomenon arising from the coordinated activity of multiple brain regions, each contributing its own piece to the puzzle of duration. But how does it work? How do neurons which fire in milliseconds keep track of seconds, minutes, hours? One leading theory is called the internal clock model. It suggests that your brain has something like a pacemaker, a neural oscillator that generates pulses at a regular rate. These pulses accumulate in a kind of mental counter, and when enough pulses have accumulated, your brain registers that a certain amount of time has passed. The faster the pacemaker fires, the more pulses accumulate and the longer time seems. The slower it fires, the fewer pulses, and the shorter time seems. This model explains a lot. It explains why time feels different when you're bored versus when you're engaged, why time slows down in emergencies, why drugs like stimulants, which speed up neural activity, make time feel like it's dragging, and why depressants, which slow neural activity, make time feel like it's flying. But here's where it gets strange. The pacemaker isn't fixed, it's flexible, influenced by attention, emotion, arousal, even body temperature. When you're paying close attention to time, when you're watching the clock waiting for something to happen, your pacemaker speeds up. More pulses accumulate. Time feels longer. But when you're absorbed in an activity, when you're not thinking about time at all, the pacemaker slows down. Fewer pulses. Time flies. This is why a watched pot never boils. Why the last 5 minutes of a workday feel like an eternity. Why a thrilling conversation can make hours disappear. Your brain's clock is not objective, it's subjective, personal, shaped by what you're doing, what you're feeling, what you're focusing on. David Eagleman, a neuroscientist at Stanford, conducted a beautiful experiment to explore this. He took volunteers to an amusement park and had them bungee jump from a tall platform. As they fell, he measured their perception of time using a special wristwatch that flashed numbers at a rate just slightly too fast to read. The idea was simple. If time really slows down during a fall, if your brain's clock speeds up in moments of fear, then you should be able to read the numbers, but the volunteers couldn't. Time didn't actually slow down. Their perception of duration afterward, however, had changed. When Eagleman asked them how long they thought the fall lasted, they consistently overestimated. A fall that took 2.5 seconds felt like it lasted 3 or 4. Why? Because during the fall, their brains were hyperactive, recording more details, more memories, more sensory information. And when they recalled the experience, when they tried to estimate its duration, they used the richness of the memory as a proxy for time. More memories equals more time. It's not that time slowed, it's that they remembered more. And memory, not physics, is what shapes our perception of how long something lasted. This has profound implications. It means your experience of time is not a direct measurement of external reality. It's a reconstruction, a story your brain tells based on how much happened, how much you noticed, how much you encoded. A boring afternoon where nothing happens, and you encode almost no new memories, feels short in the moment, but vanishes almost completely in retrospect. An exciting afternoon where everything is new and every moment is recorded feels long both in the moment and in memory. Time for you is not what the clock says, it's what your brain decides it was. There's another curious phenomenon called chronostasis. You've experienced it even if you don't know the name. It's that moment when you glance at a clock with a second hand and the first second seems to last longer than the rest. You look and the hand is frozen, stuck, almost as if time itself has paused. Then it ticks and everything returns to normal. This isn't a broken clock, it's a broken perception. When your eyes move, they create a brief gap in visual information. Your brain, not wanting you to experience the blur, fills in the gap with an image. It backdates the image, making it seem like it was there before your eyes moved. So, when you look at the clock, your brain inserts a slightly elongated version of the first second you see, stretching it backward to cover the saccade, the eye movement itself. Time in that moment genuinely feels longer. Not because it is longer, but because your brain is editing reality to create a smooth, continuous experience of now. Now let's talk about the feeling of present, the sensation of now. How long is now? Is it a second, a tenth of a second, a fraction so brief it barely exists? William James, the father of American psychology, wrote about this in 1890. He called it the specious present. The idea that what we experience as now is not an infinitesimal point in time, but a duration, a window. Research suggests this window is about 2 to 3 seconds long. That's how much time your brain bundles together into a single experience of present. Anything shorter than that feels simultaneous. Anything longer feels like a sequence. If you hear a drum beat every second, you perceive it as a rhythm. But if the drum beats are 4 seconds apart, you perceive them as separate events. The rhythm is lost, because the beats no longer fit inside the same window of now. This explains something you might have noticed about music. A song feels cohesive, feels like it flows, because the notes and rhythms fit within these overlapping windows of present. Your brain is constantly stitching together 2 to 3 second chunks of time into a seamless stream of experience. You don't notice the stitching. You don't feel the seams, but they're there. Your consciousness is not a smooth flow. It's a series of discrete moments, each about 3 seconds long, overlapping and blending into the illusion of continuity. Like frames in a film played so fast you see motion instead of stillness. But What about longer durations? How does your brain track minutes, hours, days? That's where things get murky. Because your brain doesn't have a mechanism for directly perceiving long durations. Instead, it uses proxies, memory, events, changes in context. If a lot happens, if you move through different environments, if you have varied experiences, time feels long. If nothing happens, if you stay in the same place doing the same thing, time compresses. This is why childhood feels so long and adulthood speeds up. As a child, everything is new. Every day brings novel experiences. Your brain is encoding constantly. But as an adult, routines set in. Days blur together. Your brain stops encoding as much because it's already seen this before. And when you look back, when you try to remember the past year, there's less there. Fewer landmarks, fewer memories. Time has collapsed not because it passed faster, but because you lived less of it in a way your brain could hold on to. There's a name for this. It's called the holiday paradox. A week on vacation filled with new sights and experiences feels short while you're living it, but long when you look back. A week at home doing the same routine feels long in the moment, but short in retrospect. Time's duration depends on when you measure it, during or after, and your brain gives different answers depending on which perspective you take. Then there's flow, that magical state where time seems to disappear entirely. Mihaly Csikszentmihalyi, the psychologist who coined the term, spent years studying people in flow. Athletes, musicians, surgeons, gamers. People so absorbed in what they're doing that hours pass like minutes. Csikszentmihalyi found that flow happens when challenge and skill are perfectly balanced. When the task is hard enough to demand your full attention, but not so hard that you fail. In that state, your prefrontal cortex, the part of your brain responsible for self-reflection and time monitoring, quiets down. You stop thinking about yourself. You stop thinking about time. You become the action. And when it's over, you look up, startled, wondering where the afternoon went. Time didn't stop. You just stopped noticing it. Because your brain, fully engaged, stopped constructing the sense of duration. It was too busy doing to measure. But here's something neuroscientists have discovered recently. Your perception of time isn't just about your brain, it's about your body. Your heartbeat, your breathing, even the rhythm of your gut all send signals to your brain, and those signals influence how you experience duration. When your heart beats faster, time feels like it's slowing down. When you're calm, time speeds up. This makes sense from an evolutionary perspective. In moments of danger, when your heart is racing, your brain needs to process more information to help you survive. So it speeds up its internal clock, samples the world more frequently, and gives you the feeling that time is stretching. You have more subjective time to react, even though objectively the same seconds are passing. Researchers tested this by having people listen to their own heartbeats while estimating durations. Those who were more aware of their heartbeats, more interoceptively attuned to their bodies, had more accurate time perception. The connection between body and brain, between the physical rhythm of life and the psychological experience of time, is deeper than we ever imagined. You don't just think time, you feel it in your chest, in your breath, in the quiet pulse that underlies every moment of your existence. And this brings us to something profound. Your brain doesn't passively receive time, it actively predicts it. Neuroscientists have found that much of what you perceive is not what's happening now, but what your brain thinks is about to happen next. Your brain is constantly running simulations, predicting the next moment based on the last. And when the prediction matches reality, you barely notice. But when something unexpected happens, when the prediction is wrong, time stutters. You notice. You pay attention. And that moment gets encoded more strongly into memory. This is why time seems to slow down when something surprising happens. Not because time actually slows, but because your brain's prediction engine has failed and it's scrambling to update its model. The surprise creates a denser memory, and dense memories feel longer in retrospect. Have you ever noticed how, when you're driving home on autopilot, the trip feels instant, but when you take a new route, the trip feels longer? Same distance, same duration, but different levels of attention, different amounts of prediction error. Your brain, when it can predict what's coming, essentially fast forwards through the experience. But when it can't, when the world surprises it, time expands. This is how you can lose entire chunks of your day to routine. Your brain, efficient as always, has decided those moments aren't worth encoding. It predicted them perfectly, so it skips them, saves energy, moves on. But here's the uncomfortable truth. If your brain is constantly predicting, constantly constructing time from fragments of sensation and memory and expectation, then what you experience as now is always slightly behind. There's a processing delay. Light hits your retina. Signals travel through neurons. Your brain integrates the information, runs its predictions, constructs a coherent scene. All of this takes time, about 80 milliseconds on average. So, the now you experience is actually the past, a tenth of a second ago. You're living in the past always, and you don't even know it. The present, the real present, is always just out of reach. By the time you perceive it, it's already gone. Does that change anything? Does it matter that your now is delayed? Probably not, because everyone's now is delayed. We're all living slightly behind together in a shared illusion of presence. But it does raise a question. If your brain constructs time, if it stitches together fragments into a story, if it predicts and backfills and edits to create the feeling of continuity, then how much of what you experience is real? How much is invention? Maybe that's the wrong question. Maybe real isn't the point. Maybe what matters is that your brain, with all its quirks and delays and constructions, gives you something precious, a sense of being here, now, in this moment. Even if this moment is a fiction, even if now is always already past, it's your fiction, your past, your experience of time unique and irreplaceable, shaped by your biology, your memories, your attention, your life. And in that shaping, in that construction, something beautiful emerges. The feeling that you exist, that you persist, that you are a being moving through time, even though time in the deepest sense is moving through you. There's a place in your brain hidden deep beneath the folds of cortex, shaped like a question mark turned on its side, that holds something impossible, a map, not of where you are, but of where you've been, not just in space, but in time. This structure, called the hippocampus, is your personal time machine, not metaphorically, not poetically, but literally, in the sense that neuroscientists are beginning to understand. When you remember your 7th birthday, when you recall the smell of your grandmother's kitchen, when you revisit that conversation you had last Tuesday, you're not accessing a file. You're traveling backward through neural time, and the journey changes both the destination and the traveler. Every time you remember, you rewrite. Every time you revisit, you rebuild. Memory is not a recording, it's a voyage. And like all voyages, it transforms what it touches. In 2014, a trio of scientists won the Nobel Prize in Physiology or Medicine for discovering something extraordinary. John O'Keefe, May, Britt Moser, and Edvard Moser had spent decades studying rats, tracking their neural activity as they navigated mazes. What they found was astonishing. Certain neurons in the hippocampus would fire only when the rat was in a specific location. They called these place cells: a cell for the left corner, a cell for the food dish, a cell for the center of the maze. Together, these cells formed a cognitive map, a neural representation of space that allowed the rat to know where it was and where it had been. But that wasn't all. The Mosers discovered another type of cell grid cells in a nearby region called the entorhinal cortex. These cells fired in a hexagonal pattern, creating a coordinate system, a lattice that overlaid the entire environment. Together, place cells and grid cells gave the brain a GPS, a way to navigate not just physical space, but memory space. Because where you were and when you were, it turns out, are encoded by the same system. Let me explain. When you experience something, when you live through a moment, your hippocampus doesn't just record what happened. It records where you were and when it happened. The context, the setting, the temporal framework. Place cells don't just represent locations, they represent episodes, slices of time bound to specific places. And when you remember when you close your eyes and travel back to that moment, those same place cells fire again. Your brain recreates the spatial and temporal context, pulling you backward through neural space-time into a reconstructed version of the past. You're not watching a video, you're inhabiting a simulation, a model built from fragments stitched together by the same cells that helped you navigate when the memory was first formed. But here's where it gets truly strange. Time cells. In 2011, researchers at Boston University discovered neurons in the hippocampus that don't encode space, they encode time. These cells fire in sequence one after another, marking the passage of seconds and minutes within an experience. If you train a rat to wait 5 seconds before making a choice, different time, cells will fire at 1 second, 2 seconds, 3 seconds, and so on. The brain is literally counting time, using neural firing patterns as a clock. And when the rat remembers the task, when it retrieves that memory, the same sequence of time, cells fires again. The rat is replaying time, reliving the temporal structure of the experience. Memory, in this sense, is a form of mental time travel, not just thinking about the past, but reconstructing its timeline, its duration, its sequence. This discovery has profound implications. It suggests that your hippocampus is not just a memory storage device, it's a space-time navigation system. It allows you to move backward through your personal history, to revisit moments, to reconstruct episodes, to experience in a limited but real way the flow of time that has already passed. When you remember breakfast this morning, you're not just recalling what you ate. You're mentally transporting yourself back to your kitchen, to that specific moment in time, and replaying the sequence of events. The toast popping up, the coffee brewing, the light coming through the window. Your brain is simulating the past, and in that simulation you are briefly there again. But unlike physical time travel, which would require bending space-time itself, mental time travel has a cost. And that cost is accuracy. Because every time you remember, you change the memory. This is the discovery that shocked the neuroscience community in the early 2000s. Karim Nader's work, which we touched on earlier, showed that memories are not fixed. They're labile, unstable. When you recall a memory, it enters a fragile state called reconsolidation. During this state, the memory can be updated, altered, or even erased. It's as if the act of remembering opens the file for editing, and before it's saved again, new information can slip in. A detail from a dream, a suggestion from someone else, an emotion from your current state. The memory reconsolidates with these changes, and the next time you recall it, the altered version is what you retrieve. You don't remember the original event. You remember the last time you remembered it. Let me give you an example. Imagine you witnessed a car accident. Blue sedan runs a red light. You remember it clearly. Weeks later, someone asks you about it. Was it the red sedan that ran the light? They ask. You correct them, no blue. But the suggestion has been planted. Months later, when you remember the accident, you might hesitate. Was it blue or red? The more you think about it, the less certain you become. And eventually you might remember it as red. Not because you're lying, not because your original memory was wrong, but because the act of remembering exposed the memory to interference, and the interference, subtle and insidious, rewrote the past. This is how false memories form. This is how eyewitness testimony becomes unreliable. This is how your brain, trying its best to preserve the past, accidentally invents it. Elizabeth Loftus, a psychologist at the University of California, Irvine has spent her career studying this phenomenon. In one famous experiment, she showed participants footage of a car crash, then asked them questions. One group was asked, how fast were the cars going when they hit each other? Another group was asked, how fast were the cars going when they smashed into each other? The word smashed implied greater force, greater damage. A week later, participants were asked if they remembered seeing broken glass at the scene. There was no broken glass in the footage, but those who heard the word smashed were more likely to remember seeing glass. The language used during recall had altered the memory itself. Words became shards. Suggestions became certainties. The past, malleable and soft, reshaped itself to fit the narrative. This raises an unsettling question. If memory is reconstruction, if every recall is an opportunity for distortion, then how much of your past is real? How much of your identity built on the foundation of remembered experiences rests on shaky ground? The answer is uncomfortable, probably more than you'd like to believe. Studies suggest that even vivid, emotionally charged memories, the kind you're absolutely certain about, can be wrong. These are called flashbulb memories. Where were you when you heard about 9/11? Most Americans remember that day with crystalline clarity. The room they were in, the clothes they wore, the voice on the TV. But when researchers interviewed people immediately after the attacks, and then again years later, they found significant discrepancies. Details had shifted, emotions had changed, and yet people were just as confident in their inaccurate memories as in their accurate ones. Confidence, it turns out, is not a reliable indicator of truth. So, why does the brain work this way? Why would evolution design a memory system that's so prone to error, so vulnerable to distortion? The answer researchers believe is that perfect accuracy was never the goal. Flexibility was. Your brain doesn't need to remember exactly what happened. It needs to learn from what happened. It needs to extract patterns, generalize lessons, and apply them to future situations. A memory that's too rigid, too fixed, can't adapt, can't update, can't incorporate new information. But a memory that's flexible, that can be revised and refined, is far more useful. It allows you to learn from mistakes, to update your understanding of the world, to change your mind, literally. The cost is accuracy. The benefit is adaptability. And for most of human history, adaptability mattered more. But there's something beautiful hidden in this imperfection. Because if memory is reconstruction, if it's a creative act rather than a passive retrieval, then every time you remember, you're authoring your own past. You're deciding consciously or not, which details to emphasize, which emotions to attach, which meanings to draw. Your past is not fixed. It's written and rewritten with every recall, and that means you have more power over your history than you might think. Not the power to change what happened, but the power to change what it means, to reframe, to reinterpret, to find new understanding in old pain. This is in part how therapy works, how trauma can be processed, how people heal, not by erasing the past, but by remembering it differently, by traveling back not as a passive observer, but as an active participant in the story's meaning. Now, let's talk about childhood amnesia. Why can't you remember being 2 years old or 3? Most people's earliest memories start around age 3.5. And even those are fragmentary, hazy, unreliable. It's not that nothing happened. It's not that your brain wasn't recording. It's that your hippocampus wasn't fully developed yet. The neural infrastructure for encoding autobiographical memories, for binding events to a sense of self, over time doesn't mature until around age 3 or 4. Before that, you experienced the world, but you didn't encode it in a way that could be retrieved later. The memories might exist in some form scattered across other brain regions, but they're not accessible. They're not woven into the narrative of you. You lived those moments, but they didn't become part of your story. And without a story, without a narrative thread connecting past to present, those moments might as well not have happened at all. This points to something profound. Memory is not just about the past. It's about identity, about continuity, about the sense that you, the person reading this now, are the same person who existed yesterday, last year, a decade ago. Without memory, without the ability to travel mentally through time, that sense of continuity dissolves. You become a series of disconnected presents, each one unaware of the others. This is what happens in severe amnesia. This is what happened to Henry Molaison, the man who lost his hippocampus. He could still think, still reason, still speak, but he couldn't form a coherent self that extended through time. He was trapped in an eternal, now unable to remember where now came from or where it was going. Memory, in this sense, is what makes you you. It's the thread that stitches moments into a life. And yet memory is also fiction, a story you tell yourself about who you've been. And like all stories, it's shaped by the narrator, by your current mood, your current beliefs, your current understanding. When you're happy, you remember more happy moments. When you're sad, the past seems darker. Your brain, ever the editor, adjusts, the lighting changes, the emphasis rewrites dialogue to fit the emotional tone of the present. This is called mood-congruent memory. And it's why when you're depressed, it can feel like you've always been depressed, like happiness was a lie, like the good times never really happened, but they did. Your brain has just decided for now not to show them to you. It's rewriting your past to match your present. And when your mood shifts, when the light returns, the past will shift too. The same events will look different, feel different, mean something new. Time travel in the brain is always colored by the traveler. There's another curious feature of memory. It's better at storing the gist than the details. If I tell you a story about a man who goes to a restaurant, orders a meal, eats, pays, and leaves, and then I ask you later what happened, you'll remember the sequence. But you probably won't remember exactly what he ordered or how much he paid. Your brain has compressed the story into its essential structure, discarding the specifics to save space. This is efficient, useful. But it also means that when you remember, your brain has to fill in the gaps. And it does so by inventing plausible details. Details that fit the gist that make sense in context, but that might not be true. You remember him ordering a burger, but maybe it was a salad. You remember him paying $20, but maybe it was $15. Your brain smoothing over the gaps creates a coherent narrative, and you, trusting your brain, believe it. This is how memory works. Not by preserving reality, but by constructing plausibility. So, what does this all mean for time travel? For the idea that memory is a journey backward, it means that the past you visit is not the past that was. It's a version of the past shaped by your current self, your current needs, your current understanding. It's a simulation, not a recording, a reconstruction, not a retrieval, and yet, it's the only past you have, the only past you'll ever have, because the real past, the objective past, the past, as it actually happened, is gone, dissolved into entropy, lost to the forward march of time. All you have is what your brain can build from the fragments, and those fragments, precious and flawed, are enough. They have to be, because they're the only way you can move backward at all. But if memory is a form of time travel, imperfect and creative though it may be, then what about the other direction? What about the future? Can your brain travel forward as well? And if so, what does it find there in the vast, unwritten territory of what has not yet been? Imagine you build a time machine, not someday, tonight, right now. You step inside, set the dial to 50 years ago, and press the button. The world blurs, light stretches, and suddenly you're standing in a different time. You find your grandfather young, not yet married, not yet a father. And for reasons we won't examine too closely, you prevent him from meeting your grandmother. You succeed. They never meet. They never fall in love. Your father is never born, which means you were never born, which means you never built the time machine, which means you never traveled back, which means your grandfather did meet your grandmother, which means you were born, which means you did build the time machine, which means you did travel back. The loop closes, logic breaks, causality shatters. This is the grandfather paradox, and it's not just a puzzle for science fiction. It's a genuine problem for physics, because if time travel to the past is possible, if the equations allow it, then paradoxes like this become Not just thought experiments, but real threats to the consistency of reality itself. The question is simple. Can the universe allow you to change the past? Or is there some law we haven't discovered yet that prevents paradoxes from ever happening? Physicists have been wrestling with this for decades, and the answers they've found are strange, subtle, and profoundly unsettling. Let's start with the basics. What is a paradox? It's a situation where logic eats its own tail, where cause and effect form a loop that cannot be resolved. The grandfather paradox is just one example. There are others. The bootstrap paradox, the predestination paradox. Each one explores a different way that time travel to the past could break the rules of causality, and each one forces us to ask a deeper question. Is causality a fundamental law of the universe, or is it just a pattern? We observe a habit of nature that could, under the right circumstances, be broken. In 1990, a Russian physicist named Igor Novikov proposed a solution. He called it the self-consistency principle. The idea is elegant. If time travel to the past is possible, then only those timelines that are self-consistent can exist. In other words, you can't change the past, because the past already includes everything you did when you travel back. If you go back in time to prevent your grandfather from meeting your grandmother, you will fail. Not because the universe stops you, but because the fact that you exist means you must have failed. The timeline is a closed loop. Everything that happens has always happened. There's no such thing as changing the past, because the past is fixed, immutable, woven into the fabric of space-time in a way that includes all time travelers and all their actions. This sounds comforting. It means paradoxes don't exist. They can't. The universe won't let them. But it raises another problem. If you can't change the past, then what's the point of traveling to it? You become a ghost, an observer able to witness, but not to influence. Every action you take has already been taken. Every choice you make has already been made. You're not changing history, you're fulfilling it. And if you try to do something that would create a paradox, something will stop you. A stuck door, a missed train, a sudden change of heart. The universe, it seems, conspires to protect its own consistency. But how? How does the universe know what actions would create a paradox and which wouldn't? Is there some cosmic editor reviewing every possible timeline and erasing the ones that don't make sense? Novikov didn't have an answer. He just argued that self-consistency is a requirement, a boundary condition on any solution to the equations of general relativity that permits time travel. If a solution allows paradoxes, then it's not physically realizable. The universe simply won't let it happen. But he couldn't explain the mechanism. He couldn't say how the universe enforces this rule. It's as if the laws of physics have a built-in error correction system, ensuring that causality is never violated, even when the math says it could be. Let me give you an example, a concrete one. Imagine you travel back in time with the intention of killing your younger self. You find yourself age 10 playing in a park. You raise a weapon. You aim. And then something happens. Maybe your hand shakes, and maybe a bird startles you. Maybe a stranger walks by and you lose your nerve. Or maybe in that moment you realize that if you succeed, you'll cease to exist and the paradox will collapse reality itself. So you don't pull the trigger, not because you're weak, not because you're kind, but because the timeline you're in is the only timeline that can exist. The one where you fail, the one where your 10-year-old self survives to grow up, build a time machine, and travel back to this exact moment. The loop closes, the paradox is avoided, and you walk away wondering if you ever had a choice at all. This is determinism at its most extreme. If Novikov is right, if self-consistency is a law of nature, then free will, in the context of time travel, becomes questionable. You think you're making choices, but those choices are already written into the timeline. You can't deviate. You can't change anything. You're an actor reading a script that was finalized long before you were born. And every attempt to improvise, every effort to rewrite the ending is already part of the script. It's a deeply uncomfortable idea, Because it suggests that time travel, far from giving you power over history, actually strips you of agency. You become a prisoner of consistency, bound by the need to preserve the timeline that allowed you to exist in the first place. But there's another way to think about paradoxes, another solution proposed by physicist David Deutsch, and rooted in the many worlds interpretation of quantum mechanics. What if when you travel back in time and change something, you don't change your timeline? What if you create a new one? A parallel universe branching off from the moment of your arrival where events unfold differently. In this view, you could kill your grandfather. You could prevent your own birth. But not in your timeline, in a different one. A universe where you were never born. Meanwhile, your original timeline continues unaffected. You came from a universe where your grandfather met your grandmother. You traveled to a universe where he didn't. No paradox, no contradiction. Just two separate timelines, each internally consistent, existing side by side in the vast multiverse. This is an appealing solution. It preserves free will. It allows you to change the past without breaking causality. But it has a cost. If every change creates a new timeline, then the past you're changing isn't really your past. It's someone else's. You're not rewriting history. You're writing an alternate history. And the version of you that existed in that new timeline, the one who was never born, isn't you. It's a different person. Or rather, the absence of a person. You've erased someone who might have existed, created a world where they don't. Is that murder? Is it ethical? The many worlds solution solves the paradox, but it raises a host of new questions, moral and metaphysical, that are just as difficult to answer. Now, let's talk about the bootstrap paradox. This one is subtler, more philosophical. Imagine you travel back in time and give Shakespeare a copy of his complete works. He reads them, memorizes them, and publishes them under his own name. Years later, you're born, you grow up reading Shakespeare, and eventually you travel back in time with that same book to give to him. The question is, who wrote the plays? You didn't. You just copied them from Shakespeare. But Shakespeare didn't write them either. He copied them from you. The information has no origin. It exists in a closed loop, appearing from nowhere, circling endlessly through time, with no source, no author, no beginning. This is the bootstrap paradox. And it's not just about plays. It could apply to anything, an idea, an invention, a piece of technology. If you bring something back from the future and it becomes the basis for its own creation, where did it come from? Physicists are divided on whether this is even a problem. Some argue that the bootstrap paradox is just a feature of closed time-like curves, not a bug. If time is a loop, then some things simply exist within the loop without needing an external cause. Others argue that this violates a fundamental principle of physics, that information can't be created from nothing, that everything must have a source. But if time travel is possible, if closed loops are allowed, then maybe that principle isn't as fundamental as we thought. Maybe information can exist without origin as long as the loop is self-consistent. It's a strange idea. Unsettling, but no more unsettling than the idea that you could be your own grandfather, or that the universe might have multiple timelines branching infinitely, each one as real as the next. There's a story often told in physics circles about a time traveler who goes back to meet Isaac Newton. The traveler explains calculus to Newton in detail, then returns to the future. Newton, inspired, develops calculus and publishes it. Centuries later, students learn calculus from textbooks, one of whom becomes the time traveler who goes back to teach Newton. Where did calculus come from? Did Newton invent it, or did the time traveler? The answer within the loop is neither, and both. Calculus simply is, existing in the loop unanchored to any single moment of creation. It's a closed causal chain, and if such chains are possible, then the very notion of cause and effect, of origin and consequence, starts to blur. But here's the thing. We've never observed a bootstrap paradox. We've never found information without a source. We've never seen a closed causal loop in nature, and that might be telling us something. Maybe the universe doesn't allow these loops. Maybe there's a hidden law, a chronology protection mechanism that prevents time travel to the past, precisely because it would create paradoxes. This idea was proposed by Stephen Hawking in the early 1990s. He called it the chronology protection conjecture. The idea is simple. Whenever you try to create a time machine, whenever you try to bend space-time into a closed loop that allows travel to the past, something goes wrong. Quantum effects amplify. Energy densities diverge. The machine destroys itself before it can function. The universe, it seems, has a built-in safeguard, a rule that says no, you cannot violate causality. Not because the math forbids it, but because nature does. Hawking was only half joking when he proposed this. He acknowledged that we don't have a proof, we don't have a complete theory of quantum gravity that could definitively say whether time machines are possible or not. But he pointed to suggestive evidence. Every time physicists have found a solution to Einstein's equations that permits time travel, that solution requires something exotic, negative energy, faster than light travel, and infinite mass, things we've never observed, things that might not exist. And whenever they try to build a model that gets around these requirements, quantum mechanics steps in and ruins it. Particles behave strangely near closed time-like curves. Vacuum fluctuations explode. The math breaks down. It's as if the universe is saying, nice try, but no. And yet the equations don't forbid it. General relativity in its pure form allows for closed time-like curves. There are solutions like the Gödel metric, the Tipler cylinder, the traversable wormhole where time travel to the past is mathematically possible. The equations are indifferent. They describe what space-time could do, not what it does do. And that's the mystery. Why does the universe seem to avoid these solutions? Why haven't we seen any evidence of time travelers from the future? If time travel is possible, where is everyone? One answer is that time travel is possible, but only forward. You can slow your clock, skip ahead, into the future, ride the flow of time, dilation to a distant tomorrow, but you can't go back. The arrow is one way, and if that's true, if the past is forever closed, then paradoxes are moot. They can't happen because the circumstances that would create them can't happen. But this feels unsatisfying because the equations say otherwise. And physics has taught us again and again that when the equations predict something, we should take them seriously, even when they predict things that seem impossible. So maybe the answer is more subtle. Maybe time travel to the past is possible, but only under conditions so extreme, so rare, that we'll never achieve them. Or maybe it's possible in principle, but forbidden by a deeper law we haven't discovered yet, a law that unifies general relativity and quantum mechanics, and closes the loophole that allows closed time-like curves. We don't know. Not yet. But the fact that we can even ask the question, the fact that the paradoxes exist not just in stories, but in the mathematics of space-time itself, tells us something profound. Time is stranger than we ever imagined. Causality, that bedrock of our understanding, might not be as solid as we thought. And the universe, vast and ancient and indifferent, might have rules we've only begun to glimpse. But paradoxes, as mind-bending as they are, exist in the realm of theory. There's another kind of time strangeness that exists in your daily life, in your brain, in the moments when time seems to glitch and you find yourself wondering if you've been here before, if you've lived this exact moment already. Or if something deeper is happening, something the brain does when it tries to navigate the river of time and occasionally stumbles. There are places in the universe where geometry breaks, where space folds back on itself like a piece of paper creased in half, where the distance between 2 points separated by light years or centuries collapses to nothing, a shortcut through space-time, a tunnel connecting distant regions of the cosmos or distant moments in history, through a passage so strange, so theoretically possible, yet practically impossible, that it exists more in mathematics than in reality. These are wormholes, Einstein-Rosen bridges named after the two physicists who first described them in 1935. They didn't set out to invent time machines. They were exploring the equations of general relativity, trying to understand black holes when they discovered something unexpected. A solution that connected two regions of space-time through a throat, a bridge, a geometric structure that looked on paper like it could be traversed. If you could enter one mouth of the wormhole, you'd emerge from the other, instantly, or almost instantly, regardless of how far apart the mouths were in normal space. It was a beautiful mathematical curiosity. But Einstein and his colleague Nathan Rosen never thought it could be real. They assumed nature would find a way to forbid it. They were probably right, but the equations didn't care. And in the decades since, physicists have found that wormholes, while exotic and fragile and requiring conditions we've never observed, are not forbidden by the laws of physics. They're allowed, permitted, possible in principle. And if they're possible, then so is something even stranger. Because a wormhole doesn't just connect two places, it can connect two times. If you can manipulate the mouths, move them relative to each other, subject one to time dilation while keeping the other still, then the wormhole becomes a time machine. You enter one end in the present and emerge from the other in the past, or the future. Depending on which direction you travel, the geometry doesn't care. Space-time bent into this shape allows it. The universe, indifferent as always, says nothing. But there's a catch. There's always a catch. To keep a wormhole open, to prevent it from collapsing the instant it forms, you need something that doesn't exist, or at least something we've never seen. Negative energy. Not antimatter, which is positive energy moving backward in time, but actual negative energy. A substance or field that has less than zero energy density, that pushes instead of pulls, that repels gravity instead of attracting it. Physicists call this exotic matter. And while quantum mechanics hints that it might be possible in tiny amounts under very specific conditions, we've never produced it, never observed it in nature, and certainly never gathered enough of it to stabilize a wormhole large enough for even a single atom to pass through, let alone a human being. In the 1980s, Kip Thorne, a theoretical physicist at Caltech, and one of the architects of modern gravitational wave astronomy, took the idea seriously. He and his colleagues worked out the math. They calculated how much exotic matter you'd need. They explored whether quantum fields could provide it. They found that, theoretically, it might be possible, but the requirements were staggering. You'd need to concentrate negative energy densities greater than anything we've ever achieved in a region, stable enough to last more than a fraction of a second, arranged in a geometry precise enough that the wormhole wouldn't snap shut or explode the moment you tried to use it. It's not impossible, but it's so far beyond our current technology, so far beyond anything we can even imagine building, that it might as well be magic. And yet, the equations allow it, the math works, and that's enough to keep the dream alive. But wormholes aren't the only theoretical path to the past. There are other solutions, other configurations of space-time that might, under the right conditions, permit time travel. One of the strangest is the cosmic string. Not a physical string like the ones in string theory, though the name is confusingly similar, but a hypothetical one-dimensional defect in space-time, a flaw left over from the early universe stretched across vast distances, thinner than an atom, but denser than a star. Cosmic strings, if they exist, would be relics of the Big Bang, formed when the universe cooled and different regions of space underwent phase transitions at slightly different moments, leaving seams, cracks, discontinuities in the fabric of space-time itself. These strings would have immense gravitational fields. And if two cosmic strings pass by each other at nearly the speed of light, the space-time around them would warp in such a way that closed time-like curves could form, paths through space-time that loop back on themselves. You could, in theory, circle around the strings and arrive back at your starting point in space and time before you left. The problem, of course, is that we've never seen a cosmic string. Astronomers have looked, They've searched for the gravitational lensing effects that such objects would create, the distortions in background starlight that would betray their presence. But so far, nothing. If cosmic strings exist, they're rare, or they're far away, or they decayed long ago. And even if we found one, even if we could somehow harness it, the energy required to accelerate it to near light speed, to maneuver it into position to create the precise configuration needed for time travel, is beyond anything we could hope to achieve. It's a solution in search of a universe that might not permit it. Then there's the Tipler cylinder. Proposed by physicist Frank Tipler in 1974, this is perhaps the most bizarre time machine ever conceived. Imagine an infinitely long cylinder of dense matter rotating at nearly the speed of light. The rotation drags space-time around, with it creating a region where the geometry becomes so twisted that time itself circles. If you could build such a cylinder, and if you could fly around it in the right trajectory, you could follow a path that brings you back to your starting point in time as well as space. You'd travel backward not through a wormhole or a cosmic string, but simply by circling around this spinning mass. The math is elegant, the physics is sound, but the requirements are absurd. An infinite cylinder, infinite length, rotating at nearly the speed of light without tearing itself apart. And even if you could build it, even if you had infinite resources and infinite time, you'd only be able to travel back as far as the moment the cylinder started spinning. You couldn't visit the past before the time machine was built. It's a fascinating thought experiment, but as a practical solution, it's hopeless. And yet, these solutions exist, not in reality perhaps, but in the equations, in the mathematical structure of general relativity. And that tells us something important. Time travel to the past is not forbidden by the laws of physics. It's just extraordinarily difficult, perhaps impossibly difficult. But the door is not closed, it's ajar. Locked maybe, barricaded, but not sealed shut. And physicists, stubborn and curious as they are, keep trying to pry it open. Keep exploring the edge cases, the loopholes, the exotic configurations of matter and energy that might allow us to slip through. One of the most intriguing solutions was discovered by Kurt Gödel in 1949. Yes, the same Gödel famous for his incompleteness theorems in mathematics. He was also a physicist, and he found an exact solution to Einstein's equations that describes a rotating universe. In Gödel's universe, space-time is twisted in such a way that closed time-like curves exist everywhere. You don't need a wormhole. You don't need exotic matter. You just need to travel far enough in the right direction, and you'll loop back to your own past. It's a universe where time travel is not just possible, but inevitable, where every sufficiently long journey becomes a journey through time. Einstein was disturbed by this solution. He and Gödel were friends-colleagues at the Institute for Advanced Study in Princeton, and they would walk together discussing physics philosophy, the nature of reality. Einstein respected Gödel's brilliance, but he found this solution troubling because it suggested that his theory, general relativity, might permit things he found philosophically unacceptable: causality violations, bootstrap paradoxes, the collapse of the distinction between past, present, and future. But here's the thing. Gödel's universe doesn't describe our universe. Our universe is not rotating. It's expanding, yes, accelerating even, but not rotating. Observations of the cosmic microwave background, the afterglow of the Big Bang, show no evidence of large-scale rotation. Gödel's solution is mathematically valid, but it's not physically realized. It's a possible universe in the space of all possible universes allowed by general relativity. But it's not ours. And maybe that's the pattern. Maybe all of these time travel solutions, wormholes, cosmic strings, Tipler cylinders, Gödel universes, are mathematically possible but physically forbidden. Maybe the universe we live in is fine-tuned, not for time travel, but against it. Maybe the initial conditions, the matter distribution, the energy content, the expansion rate all conspire to prevent closed time-like curves from forming, not because there's a law that says they can't, but because the universe as it happens to be doesn't create the conditions they need. Stephen Hawking believed this. He called it the chronology protection conjecture, and we touched on it before. But it's worth revisiting, because Hawking's intuition backed by decades of research into quantum effects near horizons and singularities is that the universe protects itself, that whenever you try to build a time machine, quantum mechanics intervenes. Virtual particles fluctuations in the vacuum loop around closed time-like curves and amplify. Their energy grows without bound. The wormhole collapses. The cosmic string radiates away. The Tipler cylinder tears itself apart. The universe, it seems, has a defense mechanism, a way of ensuring that causality is never violated, not because the laws forbid it explicitly, but because the laws combined with the quantum properties of fields and particles make it practically impossible. But we don't have proof. We don't have a complete theory of quantum gravity that could definitively say whether Hawking is right. String theory loop, quantum gravity. The various approaches to unifying quantum mechanics and general relativity all have something to say about this, but none of them have delivered a final answer. The question remains open. Time travel to the past is mathematically allowed, but is it physically possible? Will we ever find a way? Or is the universe structured at a fundamental level to forbid it? Think about what it would mean if time travel to the past were possible. Not just in theory, but in practice. If someone somewhere sometime in the future builds a working time machine and travels back then, they could visit us. Now, today, or yesterday, or 1,000 years ago. And if that's possible, if time travelers from the future can reach any point in the past, then where are they? Why haven't we seen them? This is sometimes called the Fermi paradox of time travel. If it's possible, why is there no evidence? No visitors from the future? No anachronistic technology found in ancient ruins? No photographs of people in modern clothing at historical events? The absence of evidence, some argue, is evidence of absence. If time travel were possible, we'd know. We'd see it. The fact that we don't suggests that it's not. That the universe, for whatever reason, doesn't permit it. Unless, of course, time travelers are very good at hiding. Or unless time travel is possible, but only to moments after the first time machine is built. A wormhole, for instance, could only take you back to the moment the wormhole was created. You couldn't visit the past before the machine existed. So, if the first time machine is built in, say, the year 2500, then travelers from 2600 could visit 2500. But they couldn't visit us. We're too early. The machine doesn't exist yet. This would explain the absence of time travelers. Not because time travel is impossible, but because we're living before the invention of the technology that makes it possible. We're in the pre-time travel era. And if that's true, then maybe somewhere in the future, someone will build the machine, and the door to the past will finally open. But not to our past, to theirs. It's a sobering thought. The possibility that time travel might be real, but forever out of our reach. That we're trapped in the past, unable to escape, unable to visit the future, except by living through it 1 second at a time. And yet, there's something almost comforting about that. Because if time travel to the past is impossible, if the universe protects causality, then the timeline is safe. Your choices matter. Your actions have consequences. The past is fixed and the future is open. You're not a prisoner of determinism. You're not an actor reading a script. You're a participant in a story that's still being written. And that story, for all its uncertainty, for all its fragility, is yours. But even if wormholes remain theoretical, even if cosmic strings stay hidden, even if the Tipler cylinder is never built, there's another way. Time bends another way. The past intrudes on the present not through the geometry of space-time, but through the peculiarities of consciousness, where the brain's attempt to track time occasionally misfires, creating experiences so vivid, so disorienting that they feel like glitches in reality itself. You walk into a room. The light slants through the window in a particular way. Someone speaks. Their words hang in the air, familiar, impossibly familiar. You've been here before. Not physically, not recently. But somehow this exact moment, this precise arrangement of light and sound and sensation has already happened. You know what they're going to say next. You can feel it. And then they say it. And for just a second time itself feels wrong, bent, repeated. As if the universe has stuttered, played the same scene twice, and only you noticed. This is déjà vu, the feeling of having already lived. And it happens to most people at least once in their lives. Some experience it regularly, others rarely. But when it happens, it's unmistakable, unsettling, a glitch in the matrix of consciousness, a moment where the brain's sense of time breaks down and past and present collapse into a single impossible now. What is déjà vu? For centuries, people believed it was mystical, a sign of past lives, a premonition, a glimpse into parallel timelines. But neuroscience has a simpler, stranger explanation. Déjà vu is a memory error, a misfiring in the brain's systems for encoding and retrieving experience. It's not that you've lived this moment before. It's that your brain is treating a new experience as if it were a memory, tagging it incorrectly with the feeling of familiarity. You're not remembering the present, you're misremembering it. And the result is a profound sense of temporal dislocation, a feeling that time has looped even though it hasn't. Akira O'Connor, a psychologist at the University of St. Andrews in Scotland, has spent years studying this phenomenon. In 2016, he and his colleagues developed a method to induce déjà vu in the lab. They used a memory technique involving word lists carefully designed to create a situation where participants felt like they'd heard a word before, even though they hadn't. Then, while the participants experienced déjà vu, the researchers scanned their brains using functional MRI. What they found was fascinating. Déjà vu didn't activate the memory regions as you might expect. Instead, it activated the frontal lobes, particularly areas involved in decision-making and conflict resolution. The brain wasn't remembering. It was detecting an error, a mismatch between the feeling of familiarity and the knowledge that this is new. Déjà vu, O'Connor suggested, is the brain catching itself in the act of making a mistake. And the feeling you get, that eerie sense of repetition, is your frontal cortex saying, wait, something's wrong here. But why does it happen? What causes the error? One leading theory involves the medial temporal lobe, the region that includes the hippocampus. We know this area is crucial for forming new memories and distinguishing between similar experiences. When it works correctly, it tags new events as new and old events as old. But sometimes the system glitches. A new experience might trigger the same neural pattern as an old one, especially if the two are similar in context, setting, or sensory details. Your brain recognizing the pattern generates a sense of familiarity. But there's no actual memory to retrieve, so you're left with the feeling of having been here before, combined with the certainty that you haven't. The conflict creates déjà vu, a temporal paradox in miniature confined to the 3 pounds of tissue inside your skull. Interestingly, déjà vu is more common in young people. It peaks in adolescence and early adulthood, then declines with age. Why? One possibility is that younger brains are more plastic, more active, more prone to creating and reorganizing neural connections. That plasticity, while useful for learning, also increases the chance of wiring errors, of patterns overlapping, of the brain mistaking similarity for identity. As you age, your brain becomes more stable, less flexible perhaps, but also less likely to glitch. Déjà vu fades not because your memory improves, but because your brain stops making the kinds of mistakes that create it. There's another phenomenon less common but equally strange called jamais vu, the opposite of déjà vu. Instead of the unfamiliar feeling familiar, the familiar becomes alien. You look at a word you've written 1,000 times, and suddenly it looks wrong, misspelled, foreign. Or you walk into your own home, and for just a moment it feels like someone else's. The sense of recognition is gone. You know intellectually that this is your house, your word, your life. But the feeling, the visceral sense of knowing, has vanished. Jamais vu is rarer than déjà vu, but it follows a similar logic. It's a disconnect between different memory systems, between explicit knowledge and implicit recognition. Your semantic memory, the part that stores facts, knows this is your home. But your perceptual memory, the part that generates feelings of familiarity, has temporarily shut off. And the result is a kind of temporal amnesia, not forgetting exactly, but a failure to feel what you should feel. Both déjà vu and jamais vu point to something profound. Your sense of time, your feeling of continuity is not a given. It's constructed, built moment by systems that can fail. When they do, time becomes strange, looped, fractured, alien, and you're reminded in the most visceral way that your experience of reality is not reality itself. It's a model, a simulation, a best guess assembled by a brain that's doing its best but is far from perfect. Now, let's talk about premonitions, the feeling that you know what's going to happen before it does. Have you ever thought of someone out of the blue and then they call or dreamed about an event only to have it occur days later? These experiences feel magical, psychic, as if you've somehow accessed the future, reached forward through time, and pulled back a fragment of what's to come. But before we attribute this to anything supernatural, let's consider what the brain is actually doing. Because your brain is in a very real sense a prediction machine. It doesn't just passively receive information. It constantly generates expectations about what will happen next. And when those expectations come true, you barely notice. But when they come true in a surprising or emotionally significant way, you remember, you pay attention, and the prediction, mundane though it might have been, starts to feel like a premonition. Psychologists call this confirmation bias. You have thousands of thoughts each day. Most of them are wrong. You think of someone and they don't call. You dream of an event and it doesn't happen. But you forget those instances. They don't register. Then once in a while, a prediction comes true. Someone does call. The event does happen. And because it's surprising, because it stands out, you remember it. You give it weight. You start to believe that you saw the future. But statistically given, the sheer number of thoughts and dreams and idle predictions you make, some of them are bound to match reality by pure chance. It's not that you can see the future. It's that you're noticing the hits and ignoring the misses. The brain bias toward pattern recognition loves to find connections, even when those connections are illusions. But there's something deeper happening too. Your brain is constantly running simulations of the future. It has to. Survival depends on anticipation, on predicting where the prey will run, where the predator will strike, when the weather will change. This predictive machinery is so fundamental, so deeply wired, that you're often unaware it's running. But it is. Every second, your brain is modeling the next moment, the next minute, the next hour, based on past experience and current context. And most of the time, those predictions are accurate, not because you're psychic, but because the world is to a certain extent predictable. People behave in patterns. Events follow sequences. And your brain, having observed those patterns, can extrapolate, can guess with reasonable accuracy what comes next. This is why you sometimes feel like you know what someone's about to say before they say it. Not because you're reading their mind, but because your brain, having listened to thousands of conversations, has learned the rhythms, the cadences, the likely responses. It's filling in the blanks before the other person finishes. And when it's right, when the prediction matches reality, it feels like clairvoyance, but it's not. It's just pattern recognition running in the background, faster than conscious thought. Dreams complicate this, Because dreams are where the brain's predictive systems run wild, unconstrained by sensory input, free to explore possibilities, rehearse scenarios, simulate futures both likely and absurd. Some researchers believe that dreams serve an adaptive function, that they allow you to practice responses to potential threats, to work through unresolved problems, to consolidate memories in ways that prepare you for what might come. If that's true, then dreams are in a sense simulations of the future, not accurate predictions, not visions, but explorations of possibility space. And occasionally, by sheer chance, one of those explorations aligns with reality. You dream of a car accident, and the next day you see one. Not because you predicted it, but because car accidents are common and your brain anxious about driving simulated one in your sleep. The match feels profound. But it's coincidence, wrapped in the illusion of meaning. There's a concept in cognitive science called chronesthesia, the ability to mentally travel through time. Not physically, not literally, but in your mind where you can revisit the past, imagine the future, and experience both as if they were present. Endel Tulving, the psychologist who coined the term, argued that this ability is unique to humans, or at least far more developed in us than in other animals. We don't just remember, we re-experience. We don't just anticipate, we pre-experience. We live in the past and future as much as we live in the present. And this capacity, this mental time travel, is what makes us capable of planning, of learning from history, of imagining alternatives. But it also makes us vulnerable to temporal illusions, to the feeling that we've been here before, or that we know what's coming, even when we don't. Your brain prioritizes prediction over accuracy. This might sound backwards, but it makes sense from an evolutionary perspective. It's better to predict that the rustling in the bushes is a predator, even if it's usually just the wind, than to assume it's nothing and get eaten. False positives in the calculus of survival are cheaper than false negatives. So, your brain errs on the side of caution. It overpredicts, overinterprets, overconnects. And in doing so, it creates experiences like déjà vu, like premonitions, like the sense that time is not a straight line, but a tangle looping back on itself, folding, intersecting. These aren't glimpses of other timelines. They're artifacts of a predictive system, optimized for survival, not truth. But here's where it gets interesting. Some people experience these phenomena more intensely than others. Studies suggest that individuals with higher levels of dopamine activity, the neurotransmitter associated with reward and pattern detection, are more prone to déjà vu, more likely to see connections that aren't there, more susceptible to the feeling that they've predicted the future. This is the same neural system implicated in creativity and insight, in the ability to see relationships between disparate ideas. The brain that glitches is also the brain that invents, that imagines, that dreams. And maybe that's the trade-off. A mind capable of profound creativity is also a mind prone to temporal confusion, to seeing patterns where none exist, to believing it has touched the future when it's only guessing the present. There's a common mistake people make. They assume that because an experience feels profound, it must be true. That because déjà vu feels like time travel, it is time travel. That because a premonition feels like foresight, it is foresight. But feelings are not evidence. Feelings are interpretations. Your brain encountering a glitch, a mismatch, an unexpected alignment generates an emotion, a sense of significance. And that emotion, powerful and convincing though it may be, is just another product of neural activity. It's not a window into hidden dimensions. It's a signal that something unusual is happening in your brain. And that's worth paying attention to. Not because it's supernatural, but because it reveals how fragile, how constructed, how dependent on the proper functioning of billions of neurons your sense of reality truly is. And yet, there's beauty in this fragility. Because if time can feel looped, if the future can feel accessible, if the past can feel present, then maybe the rigid distinction between past, present, and future is not as absolute as we think. Not in physics, where space-time is a unified whole, and not in consciousness where memory and anticipation blend into a continuous stream of experience. You are in every moment a being stretched across time, carrying the past in your memories, projecting into the future with your expectations, and living always in the fleeting now that connects them. Time glitches in this sense are reminders, hints, whispers from the brain that time is not what it seems, that the line between then and now, between here and what's coming, is thinner than you imagine. So, when time bends in your mind, when the present feels like the past, when the future feels like it's already happened, don't dismiss it. Don't fear it. Observe it. Because in that moment, you're experiencing something profound, not a violation of physics, but a revelation of biology, a glimpse into the machinery that constructs your experience of time. And that machinery, for all its flaws, for all its glitches and errors and beautiful mistakes, is what makes you human, what makes you conscious, what allows you to stand in the present and reach with thought alone, backward into memory and forward into dream, bridging the vast expanse of time with nothing but the electricity of your mind. But all of this memory and prediction, entropy and relativity paradoxes and glitches leads us back to a single question. A question that's been lurking beneath every section, every fact, every theory we've explored. And it's time at last to face it directly. What is time really? After everything we've explored, after traveling through Einstein's equations and the folds of your hippocampus, after wandering through paradoxes and wormholes, and the strange glitches of consciousness, we return to this question. Not because we haven't answered it, but because every answer leads to another question. Every discovery reveals another mystery. Time, it turns out, is not one thing. It's many things. A dimension in space-time, a direction defined by entropy, a construction of neurons, a feeling, a memory, a prediction, an illusion, and somehow, impossibly, all of these at once. Physics tells us that time is a coordinate, a fourth dimension woven with the three dimensions of space into a single fabric called space-time. In this view, the past still exists. The future already exists. All moments, every moment that ever was or ever will be laid out in a vast four-dimensional landscape. You right now listening to these words are just one cross-section of that landscape, one slice through space-time. And other slices, other moments of your life exist just as real, just as present in their own coordinates. You at age 5, you at age 50, you in your final breath. All equally real, all equally there, just located at different points in the geometry of being. This is the block universe view. And if it's true, if time is just another dimension like space, then the past is not gone. It's just elsewhere. And the future is not open. It's already written, already determined, already sitting there in space-time waiting for you to catch up. But that's not how it feels, is it? It doesn't feel like the future already exists. It feels unknown, uncertain, full of possibility. And the past doesn't feel like it's still out there somewhere. It feels finished, dissolved, gone except for the traces it left in memory, in photographs, and the marks it made on the world. Your experience of time is not the experience of moving through a static landscape. It's the experience of creation, of becoming, of the present moment unfolding into existence and then immediately vanishing into the past, leaving only echoes. And that experience, subjective though it may be, is not less real than the equations. It's a different kind of real. The reality of being alive, of being conscious, of being here now in this moment, feeling time pass. Entropy gives time its arrow. The second law of thermodynamics, that relentless increase of disorder, is why you can remember the past but not the future. Why eggs break but don't unbreak. Why causes precede effects. The universe started in a low entropy state and has been sliding toward equilibrium ever since. And we, living beings, are temporary eddies in that flow. Pockets of order maintained by consuming energy, by fighting entropy, by building structure in the midst of chaos. But only for a while. only until the energy runs out, until the order dissolves, until entropy wins. And it always wins. The arrow of time is not a law you can violate. It's a law you're subject to, a law written into the fabric of thermodynamics. And your life, your consciousness, your sense of self all exist because of that arrow, because of the flow from order to disorder. Without it, there would be no change, no memory, no you. But memory complicates things, because memory is how you experience the past. And we've learned that memory is not a recording, it's a reconstruction. Every time you remember, you're building the past from fragments, and those fragments change, shift, incorporate new information, new emotions, new meanings. The past you remember is not the past that was. It's the past as filtered through your current self, through your current mood, your current beliefs, your current understanding. And that means the past is not fixed, not in your mind. In your mind, the past is fluid, editable, subject to revision. You can't change what happened, but you can change what it means. And in changing the meaning, you change the past's power over you. You become, in a limited but real sense, the author of your own history. The future is even stranger, because the future in physics might already exist. But in consciousness, it's pure possibility. It's the space of everything that could happen filtered through the lens of everything you know. Your brain is constantly predicting, constantly simulating, running models of what comes next based on patterns learned from what came before. And most of those predictions are wrong, but a few are right. And those few shape your behavior, guide your choices, allow you to navigate a world that's always changing. The future you imagine is not the future that will be, but it's the future you're preparing for. And in preparing for it, you influence it. You make it more likely. You collapse some possibilities and expand others. The future in this sense is not predetermined. It's co-created by you, by everyone, by the countless choices made in each passing moment. So, where does that leave us? Is time real? Is it an illusion? The answer, frustratingly, is both. Time is measured by clocks, by the oscillations of atoms, by the decay of particles, is as real as anything in physics. It's woven into the equations that describe reality. It's a dimension, a coordinate, a parameter that tracks change. But time, as you experience it, as a flow from past to future, as a narrative with a beginning and an end that's constructed by your brain, by your memory systems, by your consciousness. And that construction, while grounded in the physics of the universe, is also shaped by biology, by evolution, by the specific way human brains process information and generate the feeling of being present. So time is real, and time is an illusion. And somehow, miraculously, both truths coexist. There's a phrase physicists sometimes use: time is what keeps everything from happening at once. It's a joke. But like many jokes, it contains a truth. Because without time, without the distinction between before and after, the universe would be static, frozen, a single state with no change, no evolution, no story. Time is what allows the universe to have a history, to unfold, to become. And it's what allows you to have a life, to grow, to learn, to change. Time is the canvas on which existence is painted. And while the canvas might be strange, while it might bend and stretch and loop in ways that defy intuition, it's still the ground of everything you know, everything you are. Think about what we've learned. Time is not absolute, it's relative. It passes at different rates depending on speed and gravity. Your head ages faster than your feet. A clock on a plane ticks differently than a clock on the ground. GPS satellites have to account for time dilation, or they'd be useless. This isn't theory. This is engineering. This is reality. And yet you never notice. Because the differences are so small. Because your brain smooths over the inconsistencies. Because the world you perceive is not the world as it is, but the world as your brain presents it to you. A simplified, coherent, navigable version of reality. One where time feels universal, even though it's not. Time is constructed by your brain, There's no central clock in your head, no master timekeeper ticking away the seconds. Instead, time emerges from the coordinated activity of multiple brain regions: the striatum, the cerebellum, the prefrontal cortex, working together to create the feeling of duration of sequence of now. And that feeling is flexible, stretchable, dependent on attention, emotion, context. Time slows when you're afraid, speeds up when you're bored, disappears entirely when you're in flow. Your perception of time is not a direct readout of physical time. It's an interpretation, a story your brain tells based on how much happened, how much you noticed, how much you encoded. And that story changes depending on when you tell it, during or after, in the moment or in retrospect. Time for you is not a single thing. It's a multifaceted experience shaped by the machinery of consciousness. Time travel, in the sense we dream of, might be impossible. We've explored the possibilities: wormholes, cosmic strings, Tipler cylinders, Gödel universes. All of them require exotic conditions we've never observed: negative energy, infinite mass, rotating universes. And even if we could create those conditions, even if we could bend space-time into a closed loop, quantum mechanics might intervene, particles might behave strangely, energies might diverge, the universe might protect itself, ensuring that causality is never violated. We don't know for sure, but the evidence suggests that time travel to the past, if not impossible, is at least extraordinarily, perhaps insurmountably difficult. And maybe that's okay, because we already have a form of time travel. It's called memory. It's imperfect. It's unreliable. It changes every time we use it, but it's ours. And it allows us to revisit the past, to learn from it, to carry it forward into the future. Not as unchanging truth, but as living story. Have you ever noticed how, as you get older, time seems to speed up, childhood stretches on forever? Summer vacations feel infinite, but adulthood rushes past. Years blur into months, decades into moments. Why? Because as you age, you experience fewer novel events, fewer firsts. Your brain, efficient as always, stops encoding routine, stops paying attention to the predictable, and without new memories, time collapses. You look back at the past year and wonder where it went, not because time passed faster, but because you lived less of it in a way your brain could hold on to. This is both terrifying and hopeful. Terrifying because it means time is slipping away faster and faster as life becomes routine. But hopeful because it means you can slow it down, not physically, but experientially, by seeking novelty, by paying attention, by living deliberately, by encoding new memories, by making each day distinct. You can't add more hours to your life, but you can add more life to your hours. And in doing so, you stretch time, you give it weight, you make it last. Time is the only resource you can't get back. Money can be earned again. Relationships can be repaired. Health can be recovered to an extent. But time once spent is gone. This might sound depressing, but it's also liberating because it means time is precious. Every moment matters, not in some grand cosmic sense, but in the simple human sense that this moment right now is all you have. The past is memory. The future is imagination. But this moment, this present, this now is real, and it's yours. And what you do with it, how you experience it, whether you notice it or let it slip past, unnoticed, that's up to you. Science has shown us that time is stranger than we ever imagined, that it bends, that it's relative, that it's constructed by consciousness, that it flows in one direction because of entropy, that it might not be as fundamental as we thought, that it might emerge from deeper laws, from quantum entanglement or information geometry or structures we've yet to discover. But science has also shown us something else, that despite all this strangeness, despite the relativity and the glitches and the paradoxes, time is also deeply, profoundly human. It's how you organize your life, how you tell your story, how you make sense of change, And that story, subjective though it may be, is not less important than the physics. It's the meaning you give to the physics, the way you live inside the universes in different equations and create something that matters to you, to the people you love, to the moment you're in. So, what does all of this mean? What's the takeaway from this journey through time, through physics and neuroscience and philosophy and paradox? Maybe it's this: time is not your enemy. It's not something to be feared or fought or escaped. It's the medium of your existence, the structure that allows you to have experiences, to learn, to grow, to become. And while you can't control how fast it passes, while you can't rewind or fast forward, you can control how you inhabit it. You can choose to pay attention, to be present, to notice the light slanting through the window, the sound of someone's voice, the feeling of your breath. These moments, small and fleeting though they are all you have, and they're enough. They have to be, because they're real, they're now. And now is the only time that ever truly exists. Tonight, as you rest, as your brain sifts through the day and decides what to keep and what to let go, time will continue. The universe will continue expanding. Entropy will continue increasing. Atoms will continue vibrating. But you, for a few hours, will step outside the flow. You'll dream. You'll travel through memory. You'll simulate futures that may never come. And in the morning, you'll wake into the present again, into the only moment you can ever inhabit, the moment that's always arriving, always passing, always now. We've wandered through a lot tonight, through Einstein and entropy, through memory and paradox, through wormholes and déjà vu, through the physics of time and the neuroscience of consciousness. And if you take nothing else from this journey, take this. You are a time traveler, not in the science fiction sense, but in the deepest, most real sense. You carry the past inside you. You project into the future with every thought, every plan, every dream. And you live always in the present, in the space between memory and anticipation, in the moment where time for just a breath slows down enough for you to feel it, to know it, to be in it. Thank you for staying with me through this quiet exploration, for letting these ideas drift through your mind as the night settles in. Time is vast, time is strange, time is beautiful, and you moving through it moment by moment are part of that beauty, part of the universe's way of knowing itself, of experiencing itself, of becoming conscious of its own existence. Sleep well, dream gently, let time carry you forward into rest. And when you wake, when the present returns and the day begins again, remember this: you are here, you are now. And that more than anything else we've discovered tonight is the only truth that matters. Good night, and until we meet again in another quiet moment, may your journey through time be filled with wonder,